Come on in, everyone. Come on in. Come on in, everyone. Well, actually, most of you are already here. So, anybody has any questions, please go ahead and ask me or type them in the chat. Also, go ahead and chat your first and last name, so I'll have you on the roll, and we'll go ahead and get
Quick
started.
question, Professor.
Yes, sir, Micah.
I was wondering if you got my email
I
and my
saw.
Canvas message.
Let me double check that. I saw an email earlier, but I was in the middle of running errands, so I never went back to check it.
That's fine. I just wanted to make sure you got it.
Yeah, I thought I saw your name. Now I don't see it. Maybe it's just further down. Oh, yeah, yeah, yeah. Yeah, okay, yeah, I did remember seeing this one too. So, gotcha. No problem. You want to talk about it after class?
Yeah, that'd be great.
Okay, sorry about that, bud.
I
I don't
appreciate
think
it.
this, I thought this was the one I'd seen, but it was not. So my fault.
You're all right.
All right.
Uh,
Anybody else have any questions?
not a question, just a quick comment for you. I know when we had talked about, like, I made up my lab 3 with your class.
All right, yeah.
And then Dr. Johnson changed how he wanted to do it. So he wanted me to then submit the lab to him,
Okay.
not to you. So just so you know, I won't submit lab 3 to you.
No problem. That's not a big deal. Yeah, I noticed he had changed something. I think y'all went back and maybe did the electric fields lab or something because I saw
Yeah,
that equipment was out again.
yeah, I'm not sure why he changed it, but so just letting you know, I won't send the lab to you. I'll send it to him.
No problem. And if he needs, I can still grade it for him. Just tell him, let me know if that's an issue. I don't mind. I tried to meet him today. He didn't come in time for me to catch him. I thought he was there because I heard somebody talking. But anyways, I didn't get to meet him. So anyways, anybody else have anything? All right. Well, when we finished up last time, I had basically laid out many of the thermodynamic processes. For instance, isothermal, meaning constant temperature, isovolumetric, meaning constant volume. I think I remembered telling you guys that isochoric meant the same thing. So that may or may not be true. And I told y'all to look that up. And then I said I'd look it up, and I did not look it up. But I do seem to recall that isochoric meant the same thing as isovolumetric. Also adiabatic, which means no heat flow, and we also said something called a free expansion. And your book talks a little bit about free expansion. And what we discover with a free expansion is that's basically like you have uh, sort of two tanks connected through a valve, and one tank's got a gas in it, and that gas is at a certain pressure, a certain volume of gas, obviously, and a certain number of moles of gas. And the other tank is supposed to be a complete vacuum, like you sucked it out as best you could within the technological limitations that we have. But then you just open the stopcock and allow the gas to freely expand. Since it's not expanding against the pressure, there's no actual work being done. And if you make sure the two volume containers are actually really well insulated, then there's no heat being added. And then for at least theoretically, for an ideal gas, the internal energy is only, quote unquote, only a function of temperature. So the total internal energy, which is Q minus W, since Q is zero and W zero, you expect the delta E, the change in internal energy, to also be zero. And that seems to be what it is with an ideal gas. But when you actually do a real gas in there, and it's a really hard experiment to do, but the one thing Giancoli tells you is that when you do that, it actually does depend a little bit on the pressure of the gas. So or in the volume for that matter. So the internal energy at least for an ideal gas, is not 100% accurate at all values. We at least know a case called a free expansion where the internal energy actually depends on pressure, volume, and temperature. Okay, so that's just a clarification they made. And from there, we go on and we're going to, well, in principle, I would normally do some derivations, but I've decided that it's better to just give you those equations. So that's what I'm going to do now is I'm going to give you the equations that result from the normal derivation that's done. In the textbook, let me see if I can find out roughly what we're talking about. So if you look on chapter 19, section 8-1, that's subsection 8-1, it starts off with equations 19-11a and 19-11b. That's where all that derivation is spelled out. So if you guys want to figure out how to do that derivation, it's straightforward and it's sort of meaningful, but it's basically a differential equation that allows us to come up with another equation that's only valid for an ideal gas in an adiabatic expansion or an adiabatic change anyways. So I'm going to start off as if we know those results. I'll give you some of the equations, of course, because they're necessary. But what started all this is the idea of specific heat. So when we last spoke, I had shown you specific heat given by Q equals MC delta T. I had given you the latent heat as well, which is latent heat of fusion, latent heat of vaporization, latent heat of sublimation, all that good stuff. And those two equations were quite simple. They were just Q equals MC delta T and Q equals ML. What we're introducing now is it turns out you can talk about a specific heat of a gas as well. And if you look in your book, there's a table of specific heats of gases. And that table, I'm looking up I think it's maybe it's in the previous section. Yeah, I think that's where it is. I'll double check there. Yeah, it must be in the previous section. So I'm looking in the section prior to 19-8-1, and it says molar specific heats. And what you see in that table 19-4, is something really interesting. There's some values. There's CP and CV, and then there's CP and CV with capital C's. So the CV and CP are the normal specific heats, and they would be measured in kilocalories per kilogram per Kelvin degree, or you could in principle measure them in joules per kilogram per Kelvin change. And you're not supposed to put a degree on Kelvin. My fault on that. It's been speaking. But when you look at those units, they're not very good. So like you have helium has a specific heat, the lowercase version, meaning the one in kcals per kilogram per Kelvin. Helium has a CV of 0.75, whereas neon, both of which are monatomic gases, that one has a specific heat of 0.148, so almost twice as big as the one for helium. Similarly, CP, which is the specific heat at constant pressure for helium, is 1.15, and CP for neon is 0.246. But if you make the change to what we call molar specific heat, which is where the capital C and the capital C sub V and this capital C sub P comes in, those are very interesting. Specifically, the capital C with a subscript V, which is the molar specific heat at constant volume. For helium and neon, it's 2.98 for each. For other diatomic gases, it's significantly different, but check this out. N2 and O2 have capital C subscript V of 4.96, and O2 has one that's 5.03. So those are very close to each other, just like the helium and neon are very close to each other. When you get to triatomic, it starts to fall apart a little bit, like 6.8 for CO2 and 6.2 for water, and polyatomic changes significantly to 10.3. Now, if you go to the other column, which would be, again, I'm not saying you're looking at these, I'm just trying to give you the numbers so you have some idea. But if you have that table you can look at, then by all means do. So now I'm going to talk about the molar specific heat at constant pressure. And in that case, for helium and neon, it's both 4.97. For the nitrogen, which is N2, and oxygen, which is O2, it's 6.95 and 7.03. So those, again, are very, very close. In fact, what we're going to see if you actually read the derivation, if you compare the two specific heats, the two specific molar specific heats, Cp minus Cv, in other words, you take the Cp and you subtract from it the C sub V, both of which are capital, it turns out that you consistently get very, very close to 2.0 for all of those gases, excuse me. So for instance, for helium and neon, I get 1.99. For N2, I get 1.99. For O2, I get 2.00. For CO2, I get 2.03. For water, I get 2.00. And for polyatomic, in this case, it seems to be sucrose, you get 2.05. So you can see all of these are the Cp minus Cv is very, very close to 2. And then there's another quantity we use called gamma, which is Cp over Cv. Again, we're still talking capitals here. So that's capital C with a subscript P and capital C with a subscript V. Gamma is the capital Cp divided by capital Cv. And for helium, you get 1.67. For neon, you get 1.67. For nitrogen and oxygen, you do get a little different. It's 1.40 for both of those. For CO2, you get 1.30 and 1.32 for water. And you get an entirely different thing for the sucrose. I'm pretty sure that's sucrose. And I'm not sure sucrose is the right word, but anyways, sugar. So it's 1.20 for that one. So the main thing is I'm trying to tell you that if you decide to focus on specific heats, then there is a molar specific heat, which is measured like in calories. Actually, in that case, in that table, they were doing, let's double check, calories per mole Kelvin is what they were doing for the capital C's. So in that case, you get capital C with a subscript P for specific heat at constant pressure. And then for capital C with a subscript V, you get the specific molar specific heat at constant volume. Again, they're both measured in calories per mole Kelvin. Now, here's the thing. When you apply heat to a gas, the gas obviously can take in the Q, and let's remember the first law of thermodynamics is the change in internal energy, delta E internal, is equal to Q, the heat added, minus W, the work done by the gas. So if you actually take the C, capital C with a subscript V, that means constant volume, and work is equal to the integral of F dot dl, but F is P times A, where P is the pressure and A is the cross-sectional area. So the integral of P A dl, which was the integral of F dV, or F dl, becomes P times the integral of dV, the volume. So if the volume doesn't change, no work can be done. So you expect CV to be markedly smaller than CP. And that's exactly what the case is. If you look at the CP, what happens is in that case, it's constant pressure. So the work is very specifically defined to be P times the change in volume. So when you add heat to a gas at constant pressure, then the heat can come in through Q, and that can increase the internal energy, which for ideal gases, that generally means changing the temperature. But it can also do something else, and that is specifically it can do work. So you are literally wasting some of the energy. If you're applying heat to a actual gas to raise its temperature, doing so at constant pressure is sort of wasting heat because some of the heat is going to go into doing work, which you didn't really care for. Whereas specific heat at constant volume, all of it's going just in a change in temperature. So what you find is CV is consistently smaller than CP. So those are big concepts and stuff that you should know. So now what I'm going to do is go ahead and share my screen with you guys and start off writing these equations that are important. And I'm not going through the full derivation, but if you want to, like I said, turn it to section 19-8-1 to see it. So let me start by sharing my screen. So I've turned it on and it should be coming visible any second now. Okay. So we already learned specifically what lowercase specific heat was. So for instance, we had Q is equal to MC delta T. And I told you earlier, we also had Q is equal to ML, where L could be the latent heat of vaporization, the latent heat of fusion, the latent heat of sublimation, or whatever. What we're introducing now is a new quantity. And one way of introducing it is M times C. Actually, let's do lowercase first. M times CP times delta T. And then there's another one, Q is equal to M times CV delta T. But these C's vary greatly from one gas to the next. So what was done is we started looking at the capital version, which would be Q is equal to N, the number of moles, times capital C with a subscript P delta T, and Q is equal to N capital C subscript V delta T. So when we introduce these, then we get what's called the molar specific heat. Okay, so that's one of them, and that's one of them. Now, remember, with all this going on, we also have delta E internal is equal to Q minus W, and we've got work is equal to the integral of F dot dl. But if we're talking about pressure, we don't have to worry so much about vector quantities. We only have to worry about basically moving parallel to the piston chamber that the gas is in, and then the piston head going up and down along that. So we can replace F with basically the force parallel to the axis of the cylinder, and DL with DX or DY or whatever you want, again, parallel with the axis of the cylinder. So this is going to become the integral of P times A times dXA. Well, if you think of area as the cross-sectional area of the piston, and then the piston goes downward or upward, then what you see is the area times the dx or the dy or the dz, whatever you use, that area times dx, dy, or dz is actually the volume. So this is actually the change in volume dV. So we end up getting work is equal to the integral of P dV. So with that in mind, you see that CV implies constant V, and of course, that implies work equals 0. So with that in mind, you can then say, okay, well, I know Q is equal to, so I'm going to go back to my original equations. I can say I know Q, which is equal to N times CV times delta T, is also equal to delta E internal. Okay. And the reason why it's equal to delta E internal is because W equals 0. Now, in the other case, you can say Q is equal to N CP delta T. And in this case, what we see is this is delta E internal, but it also has plus W, which for constant pressure is P delta V. Okay. So these two equations allow you, for instance, to set the E and delta E internal equal to each other, and you can get some useful expressions. But the main thing that you're going to get ultimately is that you're going to get a differential equation you can solve. You're going to get a relationship for CP minus CV and all sorts of stuff like that. So for starters, let me show that CV is just equal to the molecular weight times C lowercase v, and CP is the molecular weight times C lowercase c times P. So that just tells you how you can get them. No big deal there. We also are able to find that CP minus CV, these are capitals, by the way, is actually equal to R. And if we follow through with the derivation enough, what we'll discover is CP turns out to be 5/2 R. And then, of course, that means CV has got to equal 3/2 R. And just like I said, we expect the C at constant pressure to be larger than the C at constant volume, specifically because, like I said, when heat comes in and it's constant pressure, work can be done. So some of the heat's going into doing work through the equipetition theorem, and some of the heat's going in to change temperature. So you can sort of think of from the first law of thermodynamics, you can think of heat coming in having two different venues. In fact, there's all the modes or all the degrees of freedom of translational motion for the atoms or molecules. All of those are each a degree of freedom. So you have an X degree of freedom, a Y degree of freedom. So X would be maybe left, right, Y would be up, down, and Z would be in, out. You're full. That's it. That's the full 3 dimensions. So there's 3 degrees of freedom that correspond to temperature. It's those 3. And then there's another one that corresponds to basically doing work. We don't normally uh, discuss that like a degree of freedom, but the main thing is you can use that as an analogy or a narrative to understand that when I put heat in, I've got 3 cycles that allows me to change the temperatures, and then I got 1 cycle that does nothing to the temperature. So it's obviously going to take some of the heat away to do that work thing. When you do C sub V, however, the volume is constant, so the work is 0. Okay. So this work equals PDV. For constant pressure, that P just comes out in front, and you get work is equal to P times delta V. So I'll just say that. Oops. I'll write that over here in red just to keep our mind on it. So CP implies work is P delta V. Okay. So that's what's going on with that one. Now, all of this gives me the fact that CP minus CV is equal to R, that CP is equal to 5/2 R, and CV is equal to 3/2 R. And all of this is essentially coming from the idea that, well, it just comes from the idea of the first law of thermodynamics and then the definitions of these processes. So, like in this case, we're going to be talking about an adiabatic process eventually. Now, if we continue on with this derivation, not only do we get, like I said, CP minus CV is R, that CP is 5/2 R, and then that CV is 3/2 R, you can ultimately get, at least for a monatomic ideal gas, you're going to get delta E. Oops, let me write this down in black again. We're going to get delta E internal is equal to 3/2 nRT. That's one way. Actually, that's 3/2 nR delta T. Or another way you can write that is N times CV times delta T. And that's actually the part of the derivation where we figure out that CV is the 3/2. So the big thing that we're using here, obviously, this equation and this equation are ones we already knew. These are ones we already knew to some extent because they're the same as this one. But this is the new version, and to find these new versions of specific heat, we're going to use these quantities. Now, all this stuff right here is just me starting off the derivation. This is me getting a result. This is, again, me getting a result, and this is, again, me getting a result. But this right here is another way of writing out the change in internal energy. Now, once we've done all this, then we can go a little further and make the differential equation that needs to be solved. We have to introduce, like I said, the equal partition theorem, which basically says for each degree of freedom, the same amount of energy is going to be allotted to it. It's just basically like a law of really large numbers. So our degrees of freedom, at least at lower temperatures, we think that pretty much all that can happen is the molecule or atom for the gas can move left, right. That's one dimension. It can move in, out. That's another dimension. And it can move up, down. That's a third dimension. Each of those are not only dimensions, we call them degrees of freedom. And if you don't get much higher than, say, 70 Kelvin or something like that, then no other degrees of freedom are actually going to be engaged. And when you put heat to the system, the equal partition theorem says exactly 1/3 is going to go to left-right motion, exactly 1/3 is going to go to in-out motion, exactly 1/3 is going to go to up-down motion. But if you, in fact, go a little further, then you can get even more degrees of freedom engaging. And I'll refer you to figure 1917. So I'll say C figure 19-17. And when you see that, what you're going to see is going to, like I said, around 70 Kelvin, the only thing that engages is the three translational kinetic energies. However, if you get up above, let's say 100 Kelvin, you're starting to get the rotational kinetic energies into play. And that means, for instance, if you have a diatomic molecule like this, we have the diatomic molecule being able to move forward and backwards. That's 1 degree of freedom. Up and down's another. And then left, right's another. But once we get over 100 Kelvin, somewhere in the range from 100 to 200 Kelvin, rotational kinetic energy kicks in. So that means you could rotate it about this axis, an axis straight this way, but you can also rotate it about an axis this way. You could, in principle, rotate it about an axis that way, but that's insignificant because it's literally the width of the molecule around that dimension is just the radius of the atoms themselves. So that's really small. Now, if you keep on going up around 1,000 Kelvin, it kicks up again, and by the time you get to about 2,000, 2,100 Kelvin, somewhere around there, then the vibrational energy kicks in, and you have, for instance, two molecules can vibrate this way. Okay, so slowly but surely you end up adding all these extra degrees of freedom, and then not everything that you are applying goes straight to the translational kinetic energy, and it's the translational kinetic energy that makes up the temperature. So that's what that diagram helps us with, in addition to making sense of the equal partition theorem. Now, from that, we can go on and derive the what happens from adiabatic expansion. So again, if we start off with I'm going to start, this time I'm going to start with black. So this is adiabatic. I'll start with blue, sorry. Adiabatic expansion. So this is an outline of some of the equations that will be used in coming up with our derivation. So what we know is the first law of thermodynamics says the change in internal energy. Now remember, this is an actual differential. You're allowed to write that as a differential. This other part, you can't write a differential for Q, so I advised you we'd write d bar Q minus d bar W. And again, the reason is that d bar Q suggests you could integrate, if it wasn't for the bar, suggests you could integrate dq and get some q as a function of temperature, volume, all that stuff. There's no such function. Okay. So we have to put a bar on it to let everybody know, hey, this is not something you can integrate. Same thing with the work. There's no work function. There's no W that depends on pressure, volume, number of moles, temperature, that kind of stuff either. So we just blindly are going to use it as d bar Q and d bar W. Now, since it's adiabatic, that means dq is equal to 0, because adiabatic means no heat is allowed to enter or exit the system. So now I've got dE internal is equal to negative d bar W, which we can further specify that by realizing this is just negative P dV. Now that dV is acceptable. Again, you don't necessarily think of a volume function, but if you solve the ideal gas law for V, you'd get nRT over P. So in that sense, yeah, you do have a volume function. So what we have now is the change in internal energy is equal to negative PV, but the change in internal energy is also equal to, remember what we had in the previous thing, we actually had that the Q would be equal to dE internal, specifically right here from, let me highlight it, that right there, we can now say dE internal is equal to N times CV times, instead of delta now, we're going to use a dt. So that works fine. We can also now take that and combine that with the dE internal that we just got, so that we have N CV dt plus P dV is equal to 0. So we're getting there to some extent. We can also take the idea that P times V gives us a differential that could be written as P dV plus V dP. That's another way of writing it. And when you do that, you'd get nR dt. But if you follow this derivation on, what ultimately is going to happen is you get a dP over P plus gamma, which I've defined a few minutes ago in words. I'm going to give it to you in a second, times dV over V is equal to 0. And that's the differential equation that we're shooting for. And gamma is defined to be Cp over CV. Again, the capital's there. So this is very much an important equation we need, just like the Cp minus Cv was earlier. This part right here, the differential equation that I have, that's only important in the sense that we need to integrate it to get the rest of the result. I think you all know what the integral of dP over P is. Anyone? The question is the integral of dP over P. So anybody know what that is? Maybe someone chatted it. They did not. Okay. So anyways, the integral of, and this is the way I remember it, the integral of P to the -1, that's that weird one, right? Because the formula for integration is you take the exponent and add 1. Well, if you added 1 to an exponent of -1, you get a 0. So you're kind of left with, oh, I don't know what to do. That's when I remind myself, oh yeah, that means it's the natural log. So this one's going to be the natural log of P. And specifically, it's going to go from, let's say, P sub A to P sub B, which means P sub B, P sub A, which equals the natural log of PB over PA. So with that in mind, that's ultimately where we're going. But the cool thing is we ultimately just get this result. We get P times V to the gamma power is equal to a constant for an adiabatic process using an ideal gas. So before we already had this idea that we could say P1 V1 is equal to P2 V2, or we could say P1 V1 over T1 is equal to P2 V2 over T2, or we could say P1 over T1 is equal to P2 over T2. These are all things we could write. But now, for an adiabatic process, we can write P1 V1 to the gamma is equal to P2 V2 to the gamma, where the conditions of P1 and P2 are irrelevant as long as it's for an adiabatic expansion in an ideal gas. Okay, that looked terrible. Let's do this. Adiabatic expansion with an ideal gas. Okay, so that's the new equation that we were really shooting for. Okay, nothing new beyond that, and these CP minus CV being R and CP being 5/2 and CR being, or CV being 3/2 R. So that's the extent of the new information that you need. Now you just need to know how to use it. So this example right here is very similar to example 19-15. So I'm going to say example like 19-15 from your book. Now you'll see that it's not significantly different. It's just I changed some numbers. I have no idea how it's going to work out. I've worked the problem 1,000 times, but I'm trying to give you basically slightly different numbers so that you can look at it and stuff of that sort. Now the big question is here, this diagram tells everything that we're doing and everything that we quote unquote know. So all we know is that a gas has a volume of 1 cubic meter at point A, and it's under a pressure of 100 kilopascals and at a temperature of 300 Kelvin. Since we have all that information, we then know that going from A to B is going to be an adiabatic. In this case, can anybody tell me whether it's an adiabatic expansion or an adiabatic compression?
Would it be a compression?
Yes, it's a compression because it went from 1 cubic meter to something smaller than a cubic meter. At that point, at point B, in other words, the pressure is now 200 kilopascals instead of 100. We don't know what the volume is, but that's part of the question that we're being asked is what is the volume there? And then from point B, which we ostensibly will have the volume of pretty soon, there's an isothermal process that further compresses the gas down to 0.40 cubic meters. And what we'd like to know after that is what is the total work done in this process A to B to C. Now, hopefully you recall that in work equals F dot DL, the work is really the integral of F. In other words, it's the area under the F curve in F versus X, for instance. In this case, it's PDV. So in a P versus V diagram, it's the area under the curve as well. So we're talking about more or less this area right here is supposed to be the volume that we're calculating. If it was a closed loop, so you might come back, for instance, like this, and then back like that, then it'd be just the area inside. But in this case, it's not a closed loop. It just goes from A to B to C. So I'm taking those parts out. But that's basically what the area is supposed to be, is the actual work done. So let's start off with the solution for part A, which is specifically finding out what the volume VB is. So to do that, what we're going to use is our new equation, and I'm going to say that PA times VA to the gamma power is equal to PB times VB to the gamma power. Now, in this case, this is an ideal monatomic gas. So I'll write here ideal monatomic gas. So what that tells us is specifically it allows us to figure out what gamma is, because it tells us, of course, what CP and CV are. So with that in mind, we can say, actually, I should be writing that in black, so I'll write it back in black. So I'm also going to say that gamma is defined to be CP over CV, and that CP is 5/2 R, and that CV is 3/2 R, so that gamma is equal to 5/2 R over 3/2 R, which is just equal to 5/3. Okay. So now I can write PA times VA to the 5/3 power is equal to PB times VB to the 5/3 power. I can plug the numbers in now. I know this is 100 kilopascals, and the way this works is I can leave the kilo in there. It's no big deal. I also know that VA is 1.00 cubic meters, and that's raised to the 5/3 power. And then PB I know is 200 kilopascals, and you can see right and left the kilopascals cancel out. That's why it didn't matter that I had the kilo there. And then the VB is what we want to know, and that's raised to the 5/3 power. So what I'm going to do, since when you raise a power to a power, you multiply the powers, what that's going to compel me to do is I'm going to raise the right-hand side to the 3/5 power, and I'm going to raise the left-hand side to the 3/5 power. Because whatever you do to one side, you got to do to the other. There is a possibility whenever you raise the sides of an equation to an even power, in principle, you could introduce new solutions. It's usually not a problem when you do it with an odd power. In this case, I'm doing it with neither an odd nor even power, but it's just something to think about when you're solving equations. So when I raise this to the 5/2 power, or to the 3/2 power, what I'm now going to get is 100 over 200. Notice I just canceled out the units. So I went ahead and divided the 200, both sides of the equation by the 200 to the 3/2 power, or 3/5 power. So I get 3/5 there. And then I'm also going to say that this is 1.00 cubic meters. Now 3/5 times 5/3 is to the 1 power. And then all I have left on the other side is VB to the 1 power. So now we can tell that VB must be equal to, notice the units are automatically going to work out to be cubic meters. I'm going to pull my calculator out. And what I'm going to do is I'm going to raise 0.5 to the 3/5 power. So 0.5, I'm raising that to the parenthesis 3 divided by 5 power. And that gives me 0, oops. That gives me VB is equal to 0.6598 times 1.00 cubic meters. So the answer is 0.6598 cubic meters is the volume. And obviously we only had 3 sig figs at best. So this 8 is not a sig fig. And I'm going to circle this as if it's the answer for part A. Specifically, this is V sub B. Okay, and that's part A. So now we have the volume of part of the sample when you get to step B. Any questions on that part? Okay, now part B, we're going to calculate work total. Work total, well, actually, I'm going to say work total, and work total means the work from A to B plus the work from B to C. So I've got to calculate those two parts, and I'm going to use the formula that work is equal to the integral of P dV. Well, that's the work done on the system. But in our first law of thermodynamics, what we consider most important is the work done by the system, and specifically the question is asking how much calculate the work done on the gas for the whole process. So the work done by the gas, excuse me, that's supposed to be the work done by the gas, not on the gas. Sorry about that. So this is the work done by the gas. We want the work done on the gas. So what that means is work is going to equal the negative integral of P dV. So that's how we deal with that. Okay. Now we can use that same equation. We've got P A V A to the gamma power is equal to P at any time later times V at any time later. So I can actually use that to solve for P. So for instance, I can divide both sides by V to the gamma power. Like that. And when I do that, I'm going to get PA times VA over V to the gamma power is equal to P at any time later. So now, and remember, this is only for an adiabatic process. So this is only going to work for the work from A to B. So now I can say the work done from A to B is equal to the negative integral of P dV. Well, the P is going to be PA times VA to the gamma power times dV over V to the gamma power. In other words, I just separated that V to the gamma part. And I'm going to go from I'm going to go from VA to VB. Okay. Now we can also notice that the PA and the VA comes out in front. So I'm just going to say negative PA VA to the gamma power times the integral of dV times V to the negative gamma is V to the negative gamma plus 1. So I'm going to say V to the negative gamma plus 1 over negative gamma plus 1. And then I have to evaluate that at VA and VB. So what I'm going to get is negative PA VA to the gamma. All of that divided by negative gamma plus 1, which we know the actual fraction that corresponds to gamma. So I'll do that next. But what I have now is VB to the 1 minus gamma power minus VA to the 1 minus gamma power. So remember, we already found out that gamma is going to be 5/3. So 3/3 minus 5/3 is negative 2/3. So that means these little guys will be negative 2/3. Like that. And this down here will be negative 2/3 as well. Okay, because again, the gamma is 5/3, the 1 is 3/3. So if I do 3/3 minus 5/3, I get negative 2/3. So if I continue with this, all I have to do at this point is plug in these numbers, and I will get the work done from A to B is equal to 2/3 in the bottom as negative becomes a positive 3/2 times PA. The PA is 100 times 10 to the third pascals, which is newtons per square meter, of course, times VA, which is 1.00 cubic meters, and that's raised to the negative 2/3 power. And then I have to take VB, which we found was 0.6598 cubic meters. That's again with one extra sig fig. And again, I tried to fix my 3 and made it crappier. Okay. But this is raised to the negative 2/3 power. And then I got to subtract it from VA, which we know again is 1.00 cubic meters, again raised to the negative 2/3 power. So you can see that's what's going to happen when you raise a meter cubed to the negative 2/3 power. You're going to get a negative 2 power. So the m actually ends up on the bottom squared instead of on the top cubed. So that's what's going to happen. The same thing's going on with this first 2/3, even though it looks like it's multiplied, but that's just me trying to fit the room. So if I now take out my calculator, I can say 3/2, which is 1.5 times 100 times 10 to the third. Now, in this case, remember, Pascal is a Newton per square meter. And this 1.00 cubic meters raised to the negative 2/3 power is going to convert that to a meters squared in the bottom. So I'm going to get newtons per meter to the fourth from all this junk. So that's 1.5 for the 3/2, 100 times 10 to the third for the pressure, and then 1 to the negative 2/3 power is just 1. I can say 1 raised to the negative 2 divided by 3 power, and that's still going to get 1. And then I'm going to say times. In this case, I'm going to say parentheses 0.6598 raised to the negative 2/3 power. And then I got to move off that and then do minus 1 raised to the negative 2 divided by 3 power again. And now I'm going to close my parentheses, and this should give me the whole number. And the whole number appears to be 4.7, or let's say 47916. I'll call that 0.70. Okay, and that comes out in joules, because what we're going to have here is basically a newton per meter to the fourth times a meter to the fifth, which ultimately gives me the newton meter, which is a joule. And I now can box that off. So this whole thing becomes joules right here. And obviously I only have like 3 sig figs at best. The 0.6598, let's see what that is. 0.6598 raised to the negative 2 divided by 3 power. That gives me 1.319. And to 3 sig figs, that means to the nearest hundredths place. And then I subtract from that 1. So that only gives me 2 sig figs in subtraction. And therefore, I'm only going to be able to say that the 4 and the 7 are sig figs. Okay. So the work from A to B is really just going to be, the work from A to B is going to be basically 48 times 10 to the fourth joules, or excuse me, times 10 to the third joules. So I probably should just call it 48 kilojoules. Okay. Now that's just the work from A to B. The work from B to C is a little different. So now I'm going to work that. Work from B to C is again negative integral of PDV. This time it's isothermal though. So the ideal gas law, which says PV equals nRT, means that P could be given by N times R times T over V. So I'm going to replace the P in the integral with nRT over V. So this is going to be N times R times T, and then dV over V. And this is going to integrate from VB to VC. Now this becomes negative N times R times T, because that's all a constant. And in fact, since the nRT happens at an isothermal process, the temperature at T here could be the temperature at B or the temperature at C. Doesn't really matter. But I'm going to get the natural log of VC over VB. Okay. Well, the important thing is nRT just has to be equal to PV. So in this case, instead of just calling it nRT, why don't I just call it PBVB? So I'm going to say the NRT is PB times VB, because at least I know that the PB works because that's where we started from. So I could put a B on that. So now what I'm going to get is this quantity is equal to negative PB times VB times the ln of VC over VB, like that. And I can just plug these numbers in. The numbers are going to be negative. The pressure at B is 200 times 10 to the third pascals. The volume at B we found was 0.6598 cubic meters. So notice a cubic meter times a Newton per square meter gives me a Newton meter, which is a joule. So that definitely works. And then the natural log of VC, which we already know is 0.4. So I'm going to say 0.40 over VB, which we already know was 0.6598. Okay. And obviously the ln of a number less than 1 is going to be negative, so that'll make the total sign positive. So I'm going to say 200 times 10 to the third times 0.6598 times, now I'm going to type in the natural log, parenthesis 0.4 divided by 0.6598, close parenthesis. This gives me the 66 or 6,000, yeah, it's 66,042 joules. Okay. And in this case, we only have two sig figs for sure. So the 0, the 4, and the 2 isn't it, which means W total is the sum of those two. So I'm going to get 48 plus 66 gives me 114 kilojoules, and that's the total work. Any questions on that? So you'll notice your book does essentially the same problem. The numbers are a little different, but it's essentially the same problem. They get 85 kilojoules total. I did a little bigger because I went all the way down to 0.4 instead of 0.5 cubic meters. But the big deal is we can definitely do this through the same process. And you've now seen yet another result that we can use for anything that's an actual adiabatic expansion or contraction. Then PAVA to the gamma power is equal to PBVB to the gamma power. Again, the exponent's just on the V. Any questions on that, or any questions about how to solve this mathematical stuff? All right. So the remaining parts of the chapter talk about a lot of concepts that you need. So you really need to go ahead and read this entire chapter. I really, again, recommend you reading all the chapters at least once through in a skimming so that you can learn all the little facts and tidbits of information. And sometimes it's stuff like, you know, hey, why does this particular solid get less dense when it becomes a solid? As opposed to when it's a liquid, whereas most of them become more dense when they go from liquid to solid. That's one of the kind of things that you'll learn from it. Why does, like, for instance, one of my students asked me in class the other day, why is the latent heat of vaporization so much larger than the latent heat of fusion? Your book does that too. Why do solids behave the way they do? What is a free expansion? All that kind of stuff. So all that stuff you get to read. And just reading it once will probably make you think of some real physical situations that you'll now have some knowledge about. So that's good all by itself. And not only that, it also helps you with the concepts. But immediately after this type of problem, we go into section 19-10, which is on heat transfer. So to talk about heat transfer, I need to tell you that, let me stop sharing for a second. heat transfer is conducted by 3 different methods. And that's all we know of. Okay. So you can take, let's say I've got Raynaud's disease, so it makes like my hands sometimes get really cold, and it's not necessarily symmetric. So I can be really stressed out, and all of a sudden my right hand will get really, really cold, and my left hand's fine. So it's kind of weird. But the main thing is this hand being cold and this hand being hot, I can put them together, and this hot hand is going to deliver heat to the cold hand. And it's going to continue to do that. Heat is going to flow spontaneously. This is a version of the second law of thermodynamics. Heat flows spontaneously from the warm body to the cold body. So it's going to do that. Now, in this case, my hands are touching. So this mechanism of heat transfer is called conduction. Notice the word conduction has a duction, 2 syllables. The middle one, duct, sounds a little bit like the word touch. So that's what I always used when I was in grade school to remind myself which one was conduction, which one was convection, and which one was radiation. Now, there's another mechanism that happens, and your book talks about, for instance, ceiling fans and baseboard heaters and water heaters and all that kind of stuff. That's certainly valuable, but I'll tell you, we have no real equations to use with that because fluid mechanics is by necessity part of convection. But a typical scenario would involve maybe you take a heating element, which is basically, you can imagine a tungsten wire that is made so that you run a current through it, and the current actually heats up the tungsten by itself, but also doesn't allow current to escape the tungsten metal to go into the liquid. Okay, so that's sort of what you want to think about when you think about a heating element, like what we use for making coffee. If you have an automatic coffee maker, that normally has a heating element that's down submerged in the bottom of the water. That's also the same type of mechanism that you have in your hot water heater. You usually have 2, one down low and one up high. But the main thing is, with that one, what happens is you have the water, the heating element down at the bottom. It's going to heat up the water immediately around the heating element via conduction, right? Because the water immediately around the element is physically touching the actual heating element. So that's going to actually cause the water to heat up. Then that water heats up, and because it's hotter, you know that things expand when they get hotter. So the distance between adjacent molecules of the water, for instance, has now gotten bigger, and therefore the water is less dense, so it floats up. As it floats up, it can actually take that heat and deliver it to another area where the water was even colder. So it rises up and it cools as it rises, but it doesn't lose all of its heat. And then when it gets to the very top, in principle, it still has some heat that it can supply to the top layer of water. Once that heat is completely gone, then the gas has allowed its molecules or atoms to get as close together as they were, and it'll seep back down to the bottom so that it can be heated again with the element and float back up. Okay, so that's sort of the process with convection. If you think about it more in terms of the example your book gives you, it's a little bit easier to understand, except I think I like to give the water example because that's something you already know a little bit about by heating water through whether it be your water heater or your coffee maker, either one. But the big thing is water getting hotter definitely expands, except for that 4 degrees Celsius area where water behaves very badly or very weirdly. But it's very weirdly in the sense that it allowed life to survive ice ages. So even if the bodies of water on planet Earth completely froze solid, at the very bottom, they would still not freeze solid because at the very bottom, the density be the temperature be 4 degrees Celsius, because that's the most dense temperature at which water becomes dense. Or a better way of saying that is at 4 degrees Celsius, the density of water is a maximum. So at the bottom of all those frozen bodies of water, you'd find 4 degrees Celsius water that's still in the liquid state, and therefore any underwater life could still survive. Now, that's the second way. And the third way is radiation. And when we first introduced radiation in terms of the scientific community, we thought it was a wave, and we knew it was a wave. Specifically, we were thinking about light, for instance, and we didn't really understand what was doing the wiggling. Like when you talk about a wave, what you say is the water height wiggles from a really low spot in the trough of the wave to a really high spot at the crest of the wave to a really low spot like that. So that's water height is doing the wiggling when we're talking about waves. There was a couple problems with that when you thought of light and radiation from the sun, which we obviously can see the sun from the earth, so we know we're getting light, but we think we're getting other wavelengths too, or we know we are now, but back then we thought about it and we just didn't know they necessarily existed. But one of the things was we had never seen waves except in media. So, for instance, we could see wave on a string because it was on a string. We could see ocean waves because they're on the water. We could see earthquakes because they're traveling through rock or over rock and through water. So everything that was a wave tended to be a wave in some material. So they hypothesized, even though we knew space was sort of a vacuum outside of our atmosphere, they hypothesized the existence of something called the ether. So the ether was said to permeate everything and be all around space. And we set out to look for it eventually. So one of the experiments we did to look for it was we set off a beam of light this way. And before we did, we hit it in a half-centered, half-silvered mirror. So what happens when a 45-degree angled mirror that's half-silvered encounters light? The light splits up, and part of it goes straight through, and then the other part turns the angle and goes straight this way. Now, what we did is we made a mirror down here a very specific distance away, and another meter over here the exact same distance away. So what would happen is the light would shoot through the half-centered mirror, bounce off the distant mirror, and come back, and this light would do the same thing. And if we happen to be moving through some material, perhaps parallel to the light going this way, then the light would be slowed down in one direction and sped up in the other direction. And when the light got back to meet, we'd see little interference fringes where the crests of some waves were lining up with the troughs of others, and we'd get some cancellation. And that would allow us to figure out by how much the light was shifted as a result of our velocity through the ether. And then we'd take that whole experiment and turn it by like 90 degrees to make sure we just hadn't got a freak of nature by going in the one possible direction that was, say, parallel to the ether or something weird like that. When we did that experiment, we got a null result, meaning we got a result that was not what we expected. In other words, we found no shift in the wavelength whatsoever. It was like there wasn't an ether. Okay. Now, that being said, that didn't mean they were going to get rid of the ether just because it looked like there was none there. That just meant, hey, we really need the idea of an ether because we know that waves only travel through material, and we've never seen any waves traveling through anything other than material. So we really want that material to be there. So a guy by the name of Lorentz, who was a brilliant physicist that Einstein looked up to, he was quite a few years senior to Einstein, but he was a really good experimentalist and a good theorist, more so the theorist. But he was able to work out a set of equations that could explain the null result from that experiment. So when he did that ether experiment, he found out that ether could be there, but it's doing some weird stuff. So like it's compressing its physical structure. The physical structure of the ether is being compressed by its motion relative to us. And he came up with these very specific equations that explained it, and they were called the Lorentz transformations. Well, later, 1905, Einstein introduces the special theory of relativity, and he says, hey, Maxwell's equations are right here. We now know, several decades after Maxwell's dead, we know that the Maxwell equations are valid and they work. And they have a wave equation that doesn't change as a result of moving relative to your reference frame. In other words, if you take the wave equation and set it up for, the reference frame that I'm at in my house, you get an equation. If you now say, okay, I'm going to be teleported from my house into a spaceship that's flying by at, let's say, 3/4 of the speed of light, then you would expect the equation to be shifted as well. Well, the equation is not shifted. So Einstein used that to suggest that the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. And when he did that, he was afforded a chance to do a derivation by brilliance alone. And lo and behold, it gave him the exact same equation that Lorentz came up with. And he did not win the Nobel Prize for this. He won the Nobel Prize for his dang it, I'm forgetting the name of it. It's not black body radiation, it's the photoelectric effect, where he basically was one of the co-creators of quantum mechanics. He took Planck's result from quantum mechanics and explained the photoelectric effect, and that's what he won the Nobel Prize for. But that same year, he could have won the Nobel Prize for probably 3 other things. Okay, so now that we have that as a background, I will tell you that we have exactly 2 equations to use. One equation is for conduction. So I'm going to go ahead and share my screen again. I ain't got much time because class is almost over. So I'm going to go ahead and do share screen. And what I will tell you is the equation for conduction. Waiting for that to come on. So conduction, we do have an equation for, and we say that basically the heat applied divided by the time taken, Q over T, in other words, is in fact equal to, what I want you to imagine though here is, let's imagine a heat reservoir. At temperature T1. Okay. So this is our heat reservoir. Now let's imagine that heat reservoir is connected by a solid chunk of material whose cross-sectional area is A. So what that means is I have a rod, a solid rod, whose cross-sectional area is A again, and whose length is L, like this. And on this side over here, we have a heat reservoir, just like the last one, only this reservoir has a lower temperature. And that temperature is T2, which is less than T1. Okay. Well, it turns out the amount of heat flowing through that rod there is directly related to A, which means the larger that cross-sectional area is, the more heat flows per unit time. That makes sense, right? That's why they tell people if you're actually stranded, like in a blizzard or something like that, and maybe you're 2 or 3 people, it's actually better to strip down to nothing and have your bare skin against their bare skin and then wrap all up. That's because you're increasing the thermal conductivity between one body and the next by basically having a whole half of your body up against a human who happens to have another 98.6. So A allows more heat to flow so that the cold person gets warmer quicker. The other thing is the difference in temperature matters. So we're going to say T1 minus T2. The bigger that difference is, the quicker the heat flows. That makes sense, right? If one was 99 and the other one was 100, the heat's going to flow very slowly to bring them to equilibrium. And it's inversely proportional to the distance that it has to travel. Okay. Now, what we use for quote unquote the constant of proportionality is the constant that we associate with the material. So we put a K in here, and that's called the conductivity of the material. And there's a table for those thermal conductivities. So this is thermal conductivity. And you can look that up in a table. Okay. So this is the equation that allows you to figure out how much heat flows per second. So this is in joules per second or calories per second or something like that. I will tell you that in the building industry, they use a value called R, and that value is L over K. So it's the same L that we have here, and it's the same K that we have here. But when we do that, we get the R value. So for instance, you've seen in houses R13 or R19. The R19 is what you're supposed to use in 2x6 walls. The R13 is what you use in 2x4 walls. Now, your book does an example of a window losing heat. So that's a fine example. It's a very straightforward example, and it's exactly the type of example that I want you to work. Now, the other one, radiation, I'm going to give you this real quick, and then I'll let you guys go. So for radiation, there's something called the Stefan-Boltzmann law. And the Stefan-Boltzmann law basically says what I call the luminosity, because in astronomy, we would call that the luminosity. So I'm going to say the luminosity is equal to the heat flowing per unit time. In this case, it happens to be equal to an epsilon, which is called the emissivity. And that runs from 0 to 1, where 1 would be a really, really black, dark thing, and 0 would be the brightest, shiniest thing you could imagine. And then in addition to that, there's a constant called the Stefan-Boltzmann constant, where sigma is equal to 5.67 times 10 to the negative 11th, or excuse me, 10 to the negative 8th. Make sure I got the right number. 5.67 times 10 to the negative 8 watts per square meter Kelvin to the fourth. And then times the surface area, and then times T to the fourth power. So this is the equation you're going to use for radiation. And what you'll see is every emitter is also an absorber. So you almost never have that. You almost always have T to the fourth for the object minus T to the fourth for the surroundings. And you'll see an example of that where we talk about a person sitting in a locker room. And what we find is that person sitting in a locker room, it basically puts out about 120 watts. And that's why, for instance, gyms get hot after everybody fills them up. So that example, and it actually does one more as well, but those three examples at the end of chapter 19 is more than enough to show you how to do that. I'm not going to ask you any more difficult things than that. And I might even tell you a story later on about how relevant that is to astronomy. But you guys are free to go. I kept you a minute and a half, up 2 minutes. It just turned 2 minutes late. So I owe you 2 minutes. You guys have a good one. I'll wait for the last person to leave in case anybody has any questions. And thank you for coming. Don't forget to chat me your first and last name if you didn't already. I think everybody already did, though.
I have just a quick general question
Yeah, go for it, Hannah.
regarding what we chatted about last time. For like the Pearson MyLab Mastering, is there a course code like to enroll in the course? Because I think I figured out a way to get in there without having to repay, but I
Right.
would need a course code.
With the course code, this is what the publisher told me. Never give the course code out because then they'll access it without going through Canvas, and that'll prevent me from ever seeing your grades. So that's what they told me. That being said, I don't care. I'll give you the code. I don't mind that, but I was warned that I might not ever be able to get your score. So just be advised of that. As far as the course code goes.
No, I don't want to. I don't want to
yeah,
like risk that. So, okay. Was there homework due Sunday?
There was no, for you guys, it should have been done last night, if anything, but I pushed everything back. So let me look at it real quick and tell you what was due and what wasn't due. By the way, the course code is Younger 36792. Younger 36792 is the course code. All lowercase Younger. So I'm looking at the assignments, and what has happened is 18 is supposed to be due tomorrow night. That's 18,
Okay.
though. So that's stuff we already did. And 19 is supposed to be due on the 30th.
Okay, so I haven't missed because since I think last Wednesday I haven't been in my lab mastering, but I don't think I've
Gotcha.
missed anything.
Yeah, you
Okay.
should be able to get back in. Did you talk to them about getting another one, and had you bought like a short-term one instead of a full year one?
I can definitely buy the short-term game ones, but when I had the like little chat box, I haven't talked to like anybody on the phone, but like the help or whatever that they give you, like when you click on this, like if you need help and you can like chat with somebody, had directed me to this, and he said if you enter like your course code, it will be able, like, because you already have your account and you paid for your account, it should be able to add your course like under your account, and you wouldn't have to like pay again, because you've already paid.
Right. I
So
suspect though that's just going to get you in, but it wouldn't allow you to do any more assignments because your course code's no longer valid. It'll allow you to see your assignments. It just won't let you do any more, I suspect. So just,
okay.
be careful with that. But I do suspect if you are confident you bought the shorter version, the one that's not a whole year, then I suspect you're probably not going to be able to get out of buying it again.
Okay.
But let me know whatever problems you have. I'll do what I can to help you.
No, thank you. Did you see my text last night?
I
I
did
sent it kind of
see,
late.
yes, yeah, I did see one come in late, and in fact, I don't want to say it woke me up in a negative way. It's just
I'm
I
sorry.
actually I got like four of them at the same time. It was like four different students, so I remember seeing it, but I didn't even look at it, and then I completely forgot to look at it this morning. Is everything okay? I mean, I could look it up right now. Is that cool?
It's yes, it was just I thought because I went to take the practice test,
Right.
but and I realized the practice test was closed, but the online test was still open, and I thought the online test was due tonight and the practice test was due yesterday.
Yeah, the online test was due yesterday, 11:59, and that's supposed to have been when the practice test died. So what I'll do is I'm going to open both of them up. I suspect Micah might have this a similar issue. So I'll open them up and I'll have them be done tomorrow at midnight. Is that, or 11:59 tomorrow? Is that cool?
Yes, that worked. I was able to do the online test, but I know you do like the extra credit thing for the practice test. So I was hoping to get at least one or two attempts in before I did the online test, but I went ahead and did the online test and did fine.
I'll do the
Um,
practice and the other one. Micah, would that work for you too, bud?
That would work for me as well. Yeah, I'll do the practice test tonight after lab. I'm gonna
I'm
try to
not
get
going
the
to take
lab,
any
even though
points off. So yeah,
I appreciate that.
so yeah, I just the way things have been going with getting mixed up and stuff like that. I don't think it's worthwhile to take any points off for missing it this time. So I'll go ahead and just open them back up till tomorrow at 11:59 p.m. Uh,
Okay,
and that's the practice test and the other one. So yeah, make sure you get the practice test done too.
yeah. Okay.
awesome.
All right,
Thank you. I appreciate it. I'm going to lab.
all right. Have a good one. Good
Same.
luck, you guys.
Thank you.
Thank you.
Bye bye.